So last class we talked primarily, oops, let me minimize that. Okay, last class we talked about, of course, the Hall effect, which is here. I'll just review that quickly. The Hall effect was an approach to measure the mobility of the majority carriers. Right? We apply a magnetic field, you apply a voltage, you get a built-in field, you calculate the mobility that way. Okay, so it's a very important characterization tool. And all of this is assuming just drift, right? So you apply a field, the carriers move. Today we are going to talk about diffusion, okay, which is the other form of current, which is here. Okay? So recall, there were 4 things we need to worry about when we talk about current in semiconductors. One is, of course, the majority carriers, minority carriers. That's pretty straightforward. Then each of these will undergo drift, which is motion under electric field, which is what we have talked so far. And second, diffusion. Both of them will undergo diffusion also. Okay? So we need to account for all 4 possibilities when we calculate current, as we will see later on. The diffusion is fairly straightforward. The basic idea is that if you have a non-uniform distribution of carriers, they will diffuse from the high concentration area to the low concentration area. This is exactly the same
Place 1 drop of food coloring into.
as molecules diffusing in a liquid. Okay? So if you have, it's kind of hard to see, but if you have a drop of concentrated molecule, if you give it enough time, it will diffuse through the volume and essentially, eventually, reach a constant concentration. Okay? And it's shown here with hot water and cold water. So it's temperature dependent, as you can see. In hot water, it diffuses much faster than in cold water. So in cold water, you can see the molecules are still, in this case, ink molecules are still localized to a small region. But given enough time, it will still diffuse. So it's basically the same principle as you see in microscopic systems. Okay? So keep that in mind as we keep going. But of course, in our case, we are talking about electrons and holes. Okay? These are molecules, so molecules in water or whatever. Or if you have a perfume in air, right? That's the other example people talk about. Okay, so if the analogous situation in semiconductors is the following. In some manner, we can generate a pulse of, let's say, in this case, electrons in a p-type material. Okay, so imagine, it doesn't have to be p-type, but let's assume p-type for the sake of argument. And somehow, instantaneously, you create a very high concentration of holes, the minority carriers, okay, in a pulse. So it's very localized. And we'll talk about how this can be done later on, but it can be done optically. For instance, you can shine a pulse of laser beam on it. It'll generate electron-hole pairs, and the holes will, you create both electrons and holes. You can also do this with carrier injection with p-n junctions, which we'll talk about in chapter 5. Okay. By the way, this is chapter 4. This is part of chapter 4. Okay. So when we look at this, the first thing to notice, okay, the axis are, the vertical axis is concentration of electrons, in this case n of x. The horizontal axis is essentially space, distance, okay, x. It's one-dimensional in this case for simplicity. So at t equals 0, let's say we create this very, very localized pulse of holes, electrons in this case. Okay, electrons generated in a very concentrated region, somehow, at t equals 0. Now, as you allow the time to progress, just like those ink molecules in water, these electrons will diffuse from very high concentration to low concentration. So imagine just like the ink molecules. Okay? And that's what happens here. At some time t1, the electrons will diffuse. Basically, they'll spread out, and their peak concentration comes down. Okay? So they've spread out, and the peak concentration has come down from here to here. And the way this happens, of course, has to do with the thermal motion. As we saw in the video, the hotter it is, it diffuses faster. Basically, the electrons will collide with lattice atoms and basically move slowly. Okay? And there's a thermodynamic reason why it goes from high concentration to low concentration. You can read about it in the text, but it's pretty straightforward. Okay? It essentially moves randomly such that it diffuses to larger volumes. Now, of course, as time moves on, it spreads out even further, shown by this, and then finally that. Okay? Until eventually it basically becomes uniform. It uniformly distributes over all available space. Just like an ink solution, right? After a while, the whole thing becomes blue or whatever. Okay, so essentially, I want you to understand this picture because once we get into the math, it becomes abstract. Okay, so keep this picture in mind as we start doing the math. Okay? Okay, one important metric in diffusion is what's called the mean free path, and we'll come back to this, but I wanted to introduce this quickly. The idea is essentially, what is the average distance that an electron travels in between collisions? So look at this electron. It's a blue electron, and then let's say there are lattice atoms shown in red. Okay, the electron is moving around randomly. It scatters from this atom, then from this atom, so on and so forth, right? It's some sort of random motion. The mean free path, essentially, if you take all the distance from here to here, and then you divide it by the number of collisions that have happened. So it's the average distance that the electron travels in between collisions. Of course, it's the number of collisions will be huge, right? There will be billions of collisions. So when you average them over lots and lots of electrons, that's a fairly good constant number. This turns out to be a very important parameter in the equations we're going to talk about. Yes?
So we're not actually talking about path distance, but just from point A to point B
by all the collisions. Yeah, why? Because they're random, right? So each of these paths will be different. There will be some random distribution of paths. What we're talking about is a normal average value.
So the
it's all statistical.
Towards well, I guess that would be the average. Okay.
Yeah, it's all statistical. All of this is based on thermodynamics, which is essentially based on statistical mechanics. Okay. In any case, let's see how that applies. So to quantify this, let's look at one half of that plot that we saw. Okay, we're basically going to only look at the positive x. Okay, it's symmetric in this particular case, and we'll talk about that later on. But it's fine. So in this case, in order to understand this, let's discretize the space. Okay, so let's look at space in small increments where the length of that increment is equal to the mean free path. Okay, of course, the logic is that within that increment, the electron on an average has no collision. If you make the distance small enough, that's the average distance between collisions. That's average no collisions, right? Again, this is all statistical, so you have to think about it that way. So imagine the distance divided into small segments, as shown here, okay, where each segment is a mean free path. So the electrons within here will undergo very few collisions within that path at some instant of time. So all of this is one snapshot in time, right? So recall, this is showing you different snapshots at time as it spreads, right? So there's a time component, but here we're looking at a specific time. Okay, we'll introduce the time later on. Okay, so that's the mean free path. So if you look closely at two of these segments, okay, let's imagine segment 1 and segment 2. There are some electrons here, there are some electrons here, they're all moving back and forth, and so on and so forth. Question is, what is the rate of the diffusion? That's what we're trying to find out. What is the rate at which the electrons move from, say, 1 to 2, and from 3 to 2, for instance? But that's the goal. That's what we're trying to model. Again, the big picture is to understand how this spreading happens. How fast does it happen? What does it depend on? And so on and so forth. That's the idea, okay? Why? Okay, let's step back a second before we go in again. Why is that important? It is important because, think about it this way. There's a high concentration of electrons here, and they have basically moved here and here. That means there is a current, right? Because the electrons have moved, there's a current in the opposite direction. We have to account for that. Okay? That's the reason we are doing this. We need to model diffusion in order to calculate what's called the diffusion current, just like we did for the drift current. Okay? Okay, so let's look at this situation. Okay, simplified situation. The two regions in space. One is x naught minus L bar, where it's here. And this is x naught plus L bar. That's x naught, and you have a region 3 here. Okay, so the electrons moving from 1 to 2, from the block 1 to block 2, in one mean free time interval. Recall mean free time was the average time between collisions. It is related to the mean free path, as we will talk about, but they're two different things. Mean free time is what we talked about before. We talked about lattice scattering as well. Okay, it's just the average time. The electrons move from 3 to 2 in one mean free time interval, and they, if you want to know how the concentration within this region 2 changes with time, that's all you need. You need the rate coming in from this side and rate coming in from this side. You add them up, that gives you the total rate of what happens to the electrons in that small interval. Okay? So let's model it. So the net flow of electrons from left to right in one mean free time is that. So N1, which is the concentration of electrons in the region 1, multiplied by L bar times A, A being the area. Okay? L bar times A is the volume, so N1 times L bar times A gives you the total number. Okay? Now, why is this the case? Because in one mean free time, the distance traveled by the electron, on an average, is L bar. Right? So that's the definition of mean free path. Mean free path is the average distance between collisions. Mean free time is the average time between collisions. Right? So in one mean free time, the electron on an average has moved one mean free path. Same thing, right? Just common sense. Okay? So of course, this is what's coming into region 2 from 1 to 2. Now, why is it coming in from 1 to 2? Because 1 has a higher concentration. You see, that's the concentration gradient, n of x. Region 1 has a higher concentration. Region 2 has a lower concentration. Region 3 has even lower concentration. So from experience, we know that the electrons will move from 1 to 2. Right? And of course, we also know that the electrons will move from 2 to 3. So when we say electrons moving from 3 to 2, that number should be negative. We know that by experience, but we'll show it. Okay? Okay, so this is the number of electrons going from 1 to 2. And this is the number of electrons going from 2 to 1. Okay, same thing. Okay, so you subtract them, that gives you the average number of electrons that are entering 2, region 2. Okay, now the same thing, the rate of electron flow. So we can write the same thing for 3 to 2 in a minute, but the rate of electron flow per unit area is so-called electron flux density, or it is essentially electron current. If you multiply that by Q, you'll get the current density. It's just you divide it by area. Okay? And time. So let's see this again. This is the number of electrons that have passed through. Okay? You divide it by area, that gives you the number of electrons per unit area that have passed through. And you divide it by time, gives you the number of electrons per unit area per unit time that have passed through, which is the rate of flow of electrons, which is what's shown here. Okay? That's the flux. So it's just this equation divided by A divided by time. T bar, which is the mean free time, average time between collisions. Okay? So again, the so-called electron flux density is the number of electrons coming into region 2 per unit area per unit time. Of course, it is related to current density, as we will see in a second. Okay, but that's the idea. Okay. Now, we will make the assumption that L bar is a very small distance, which is typically the case, unless you have very special conditions. We'll talk about those later on for very specific devices. Okay? L bar is is the average distance that the electron travels between collisions, and that's typically pretty small, nanometers. Okay? Tens of nanometers typically. It's very small. So So you can assume that's a differential distance, and we can apply calculus, differential calculus. That's the idea. Okay? So then we can write something like this. The difference in concentration between 1 and 2, which is N1 minus N2, can be written as N of x, which is the concentration here, okay, minus N of x plus delta x, which is the concentration here, where delta x is the mean free length, mean free path, okay, and divided by delta x. So that's a fractional change in concentration from 1 to 2 per unit length. Okay? We are going to put this back here, so you'll see in a second. This is N1 minus N2. That's what we're going to put it back in and apply differential calculus. Okay? So now we can write the flux density as L bar over 2T bar. Okay, that's the same thing, but now we have an extra L bar which comes from here. Okay. By the way, let me just make sure everyone's on the same page. Let's say you have a function f of x. Okay, function f. Just basic review of differential calculus. Okay, let's say you have some function. If you want to know over a small distance delta x how much the function has changed, how would you do this? Delta f, which is the change in the function, is given by df over dx times delta x. Okay. That's a basic theorem from differential calculus, right? This is exactly what we just did. Okay, we have some function here, and we have this delta x, which is equal to the mean free path. We want to know how much the concentration changed, which is N1 minus N2. Okay, so if you do that, N1 minus N2, you write it this way, and you plug it in, and then you apply the limit of delta x going to 0, then you get what I just wrote, which is basically applying the theorem. Okay, so you get the flux is now dependent on of course, there's a negative sign, right? Why is there a negative sign? Can someone tell me quickly? I can't, you have to shout. Say that again? No, I think you're right. Say it again. You're moving from 2 to 1. Is that what you said? Yeah. So it is actually, it is, the point is, that's exactly right in the sense that the electron's going from high concentration to low concentration. Okay? So if you look at this value, dN over dx, what is this? Is this positive or negative? For this example. Is n increasing or decreasing with x? It is decreasing, right? So this number has to be negative, right? This is the slope of the curve, it has to be negative. It's decreasing. Okay? What that negative sign is telling us is that the flow of electron is in the direction of decreasing concentration. It's just common sense, and that we know that's what should happen. It should go from high concentration to low concentration. That's all it's saying. Okay? So, and it's the same for holes. It has nothing to do with the sign of the electron or hole. It has to do with just diffusion. Okay, so keep that in mind. Don't get confused with the other possibility. Okay, so the electron flux now depends on square of the mean free path divided by 2 times the mean free time times the concentration gradient. Okay, dN over dx is the rate at which the carrier concentration changes. Okay, now you see something interesting. This means that even if n by itself is small, n of x can be quite small. Let's say they're minority carriers. This n of x in terms of absolute values can be, let's say it's 10 raised to 11, whereas the majority carriers are, let's say, 10 raised to 20. So we don't care. This is much larger, right? So let's say these are the number of holes, and these are the number of electrons. It's a p-type material, right? Of course, the number of holes are 10 orders of magnitude higher. So we would assume that we can ignore them completely, right? We can ignore the holes. Turns out that's not the case. It has to do with this equation. You see this? If you have a p-type material, why would I even bother with electrons? There's so few of them. 10 orders of magnitude smaller. If it was only drift current, that's exactly correct. Because drift current depends on the concentration. The drift current from electrons in this case will be 10 orders of magnitude smaller than the drift current from holes, and you can of course ignore it. But for diffusion current, it is not the concentration that matters. It is the rate of change of concentration. It's dN over dx that matters. Okay? Which means that even though you have a small number here, dN over dx could be much larger than dP over dx. It can be quite large if you have a very sharp change in concentration, for instance, which means that we need to take this into account. Okay, so do you see that physically? You need to address diffusion even though there are very, very few carriers, because it depends on the gradient. Okay, that's an important concept actually. We'll come back to that. Now this constant here is also called the electron diffusion coefficient, or D, and we'll see this again. We also sometimes put it as with an N there to say it's electrons, because we will also have a diffusion coefficient for holes. Okay. So now we can write the diffusion equation basically as electron flux is given by minus dN over dI. Very simple. Okay? And that's what we will solve. Yeah.
Is it minus dN? I mean, you circled the minus sign.
Ah, yeah, it should be minus, yeah. Now, the diffusion coefficients are always positive, yes.
Okay.
Yeah, yeah.
Thank you.
Again, don't memorize these things in terms of signs, because, for instance, I don't remember what's what. No? Think contextually, everything is very straightforward if you can follow the logic. Okay, where that sign comes from. So it's much more important that you understand where the sign comes from rather than just memorizing it. Okay. So if you ask me, I wouldn't know, for instance, unless I think about it. Okay. Oh, okay, good example problem. What are the units of the electron diffusion coefficient? Okay, take 15, 20 seconds, talk to your neighbors, discuss, and give me an answer. Okay, you should be able to do this. This is straightforward. Okay. You should talk to someone behind you. Okay, let's see. Someone tell me the answer, but not you or you. You're always done. Someone else. Not you either. Yes, Sam.
Surface area over time?
Yes. Yeah, very simple, right? It's just, you should, by the way, doing dimensional analysis is actually a very important part of this, so this is not a trivial thing. Always keep these dimensions in mind because it will help you later on check your answers and so on, right? So L bar square over 2T bar. L bar square is just the area, right? So it's centimeter squared, or meter squared, whatever, and by second. Okay, that's straightforward. Okay, so let's, okay, what does the minus sign mean? I already answered that. So keep that in mind. It is, of course, in the direction of decreasing concentration. Yes?
What does the bar mean?
Yes, okay, good question. The bar typically in physics refers to average value, okay, in general. So if I have to rigorously define these things, the way I would do it is the following. Okay? Let's talk about L bar. L bar would be some sort of integral over some large distance, okay, some x1 to x2, some big distance of the average correlations over the average distance between each correlation, okay, times like that, it would be something like this, where dx is the distance between each collision divided by x2 minus x1. So you see this is the average value, right? Average distance traveled between collisions. Of course, there will be some randomization here, random function depends on the statistical distribution. This, if you recall, can also be written that way. And with quantum mechanics, what that means is just basically you have an operator, right? So it's all related back to what we talked about. So the bar is just a way to mention that's an average. And same thing for time. Yes?
So a couple follow-up questions. First off, so that's the integral of L dx, right?
No.
No.
So I left something out here because this will be the distribution of distances due to the random collisions. So here what I'm integrating is the distance between each collision. So if you go back to the picture we had, let's go back to this picture. Basically what that integral does is that it will add up all these lengths. That's what I'm doing. Over all electrons as well. So you can typically the way this is done, you also integrate over the number of electrons as well, which is a huge number. You average over the number of electrons. So you add all these distances up for each electron, for a huge number of electrons, and average everything. That gives you an average path length. And that's a very constant number because you're talking about huge numbers here. Averages of very large numbers are very statistically accurate. Okay?
And then,
Yeah.
I don't mean to be nitpicky, but
That's
I want
fine.
to make sure I understand it.
Yeah.
Between 2 and 3,
Yes.
That L doesn't have a bar in it. It should, right?
Yeah, it should.
Okay.
It should.
That's cool.
Yeah. That's probably a typo from the text, yeah. Okay, so the idea is that we can, of course, apply the same principle for holes as well. Okay, if you have a highly concentrated region of holes, of course, they will diffuse as well. And, of course, you still have the negative sign because it has nothing to do with the charge of the carrier in this case, right? It just has to do with the fact it goes from high concentration to low concentration. You will still have a minus sign there. So the equations look exactly the same. Okay? And you can understand that logic, right? So you can write down the equations. The diffusion equations are the same. For electrons, the same as what I just wrote there. Phi n of x is minus dn over dx. For holes is phi p of x is minus dp over dx. Okay, same thing. Of course, the diffusion coefficients themselves are different, as we will see. Okay? Okay. Now, of course, this is just the rate of flow of the carriers. From this, we want to calculate the current, or the current density, right? Eventually, that's the goal. So the current density equations are given here. It's very straightforward, right? You take the flux multiplied by charge. And if it's electron, you put a negative sign, because the current flows the opposite way. Simple as that. So that's what's done. The electron, you see a minus q there, and you multiply it by this equation. And for the holes, you put a plus q multiplied by this equation. And you get the simple diffusion current equations. So again, just to review, if you recall, the drift current was q and electric field and the mobility, right? So the drift current, let me just summarize this because it's a very important point. So drift is proportional to the n or p, okay? Whereas diffusion is proportional to dn over dx or dp over dx. And you need to understand these conceptually. Okay, the equations you can always look up. In drift, you apply a field. It depends how many electrons actually are there so they can move. Nothing to do with there's no concentration gradient, right? Whereas in diffusion, everything is determined by the concentration gradient. So keep that picture in mind. Okay. So the other point, of course, which is obvious in the equation, is that the holes and electrons, of course, both of them move from high concentration to low concentration, but of course the currents are opposite directions. Because the electron's direction is opposite to the current. We all know that now, so the currents are opposite directions. Okay, so Now let's put these together, our understanding of drift and diffusion, and try to calculate the total current, which is of course a goal here, right? That's getting to being able to do that. So if an electric field is present in addition to the carrier concentration gradient, so you have not just a pulse of electrons or holes, but also an electric field, then you have both drift and diffusion. You need to account for both. Okay? Then the equations again they're just added. So the electron current density is given by the drift current, which, as I said before, is proportional to the concentration of electrons. It's Q mu, which is the mobility of electrons, times the field. Okay, that's what we saw last class. Plus the diffusion current, which is what we just saw, Q dn over dx. Pretty straightforward. For the hole current, they're opposite. The drift current is the same. It moves in the direction of the field. So the current is in the direction of the field. But the diffusion current has a negative sign because it moves in the opposite to the diffusion gradient, a carrier gradient. Okay? So keep that in mind. So this is what I've said about we had to consider 4 things when we calculate current. You have to calculate current for electrons. You have to calculate current for holes. For each electron and hole, there's a drift component and a diffusion component. So we have 4 terms to worry about. Okay, so the total current density is this plus that, 4 terms. Okay, so in any situation, if you have to calculate current, this is all we need to know. We can calculate it. Now we can understand how transistors work and all that, because now we have all the background information to do it. Okay. Okay. So. Okay. So the minority carriers, as I said before, so let's think about this a second. When you have a p-type material, let's look at these terms. Okay, let's imagine a p-type material. There are lots and lots of holes. Okay, p-type material means p is much greater than n. Okay, orders of magnitude greater, which means that if you look at these 4 terms, which term will be the most important? Right. It'll be this term, right? That's why, because P will be orders of magnitude larger than anything else here. In general, okay? But, of course, P is much greater than N for sure, so you can pretty much ignore this term. So imagine P is 10 orders of magnitude higher than N, then if you compare these two, you can basically ignore this one, right? You can ignore the electron drift in a p-type material, pretty much. Okay? But if you look at these 2 terms, you can't tell for sure, because it depends on the concentration gradient. Whether it's p-type or n-type or not, it's very hard to tell, right? You have to actually look at the situation. But in general, in a p-type material, let's say if I have a bar of p-type material, okay, there's lots of electrons and lots of holes. If I generate electron-hole pairs, let's say with light or whatever, so I generate locally lots of electrons and lots of holes. Okay. The extra electron, so remember P naught, N naught is Ni squared. So if P naught is much greater than N naught, okay, so that's the situation for the P type. And if I generate P prime equals N prime, which is the electron hole pairs, they're equal, right? Remember we knew that. This number is probably pretty small. They're the same compared to this. Okay, let's put some numbers down. So let's say P naught is 10 raised to 20. Okay, and P prime, which is the excess electrons are created, is let's say 10 raised to 10. Okay, so P prime is much smaller than P naught. Right? So it is possible that you can basically ignore the contribution of the excess holes in a p-type material because that's pretty small. Why? because the concentration gradient will now be given by P naught plus P prime. Right? Even though this could be highly localized. Okay. For n of x, if I have to write this, n naught, in this particular case, if you look at the electrons, n naught, let's say, is 10 raised to 10. Okay, that's a small number. N prime is also 10 raised to 10. So that's a big change, right? You've doubled them. So when you create electron hole pairs in a highly doped material, the minority carriers undergo a huge change, whereas the majority carriers undergo a small change. Okay? That's another way to look at what I just said before. The drift current of the minority carriers will be small compared to the majority carriers, but the diffusion current of the minority carriers can be quite significant, right? Because it depends on dn over dx, which can be even greater than, in principle, than that, because that just matters how fast it changes. It could be. It's not always the case. It could be. Okay. So again, to summarize, the minority carriers do not contribute much to drift current, but they can contribute significantly to diffusion current. And it's the same case for n-type as well, right? Just flip the things. If you have n-type, you have more electrons, and the holes become the minority carriers. So remember, you have to be very clear on the terms. Minority carriers means they are the fewer number compared to majority. We will refer to this again and again, so make sure you have a very clear picture of what those mean. Yes?
So you were mentioning that if it's a p-type material,
Mm-hmm.
then there's a very small change with the holes.
Yes,
centered
the excess
there,
holes,
so
yeah.
you can neglect that for drift.
Yes,
Right.
exactly. Because this number, so think about this. I have 10 raised to 20 here, plus 10 raised to 10.
Yeah.
What is this? This is pretty much 10 raised to 20. Yeah.
But would you still need to worry about the change in holes for the
Yes.
diffusion?
Yes, very good. That's a good point. It does. So for diffusion, we actually don't know it depends. Depends on the situation. Diffusion is a bit more complicated. So you cannot ignore any terms in the diffusion in general. You have to do the calculation and see. But typically what happens is that the diffusion, the gradients are typically different. So one typically dominates, but it's hard to tell which it could be. And we will see some examples. That's an important point, though. Yes?
So for the diffusion, you always need to pay close attention to what you're doing. For the drift, you don't need to worry as much about the
Exactly. Unless this number becomes large, then you have to. So if you have huge numbers of carriers being generated, yes, you have to worry about it. But in general, yes, you can ignore that. But of course, you look at the specific example. Okay? It's much more important to understand what's going on rather than just plug in numbers. Yeah. Okay, so we can visualize this as follows. Okay, this is actually also quite important. In fact, today, if you really need to review something and get out of it, this is the slide. You need to really understand. I would say, go back, make sure you think about this. This is the picture of what's happening. Okay, so in this case, look at the left-hand side. Okay, you have some semiconductor material. First of all, we apply an electric field. Okay, pretty straightforward. The second of all, we say that there are concentration gradients. We don't say how they're generated. They're just there. Okay, so this is the concentration gradient for electrons. So electron concentration is high on the left, low on the right. The same thing for holes, high on the left, low on the right. Because typically, they follow each other typically because you generate them as electron hole pairs. So this is a standard, typical example. Okay. Now let's look at the different currents. As I said before, we have 4 terms to worry about, 4 current terms. Okay. The dashed lines are fluxes. So we can look at the fluxes first. This is so first of all, let's look at the drift. That's the easy one. So the drift of electrons will happen opposite to the field, right? It will drift away in the opposite direction to the field. So the current will be in the direction of the field. So if you look at the drift current, that's the drift. Yes, that's the drift shown here. Okay, and the flux of electrons in the drift will be here. It's opposite. Okay, you see that? So that's how the electrons move, and that's their current. Oops, where's JN? Oh, sorry, it's down here. Confused. So you see that? This is the way the electrons move. That's the current resulting from that motion. Okay. Now let's look at the holes. It's pretty easy. For holes where is it? Okay. P. Okay. There's the hole. So the holes are moving along the field, and the current is JP drift, which is in the direction of the field as well. Pretty easy. So the drift is relatively easy to understand. But diffusion is also not that difficult. So if we look at the electron diffusion, of course it goes from high concentration to low concentration, shown here. And the current is in the opposite direction, which is shown here. Okay? And the same thing for holes. Holes diffuse from high concentration to low concentration, which is shown here. Here. And the current resulting from that is in the same direction, shown here. Okay? You have to add all the currents up to get the final current. So let's look at what the directions of the current are. The diffusion currents are both, for the holes is here. The drift current for the electrons is here. The drift currents for the diffusion current for the electrons is here. The drift current for the electrons is here. And yeah, so you can see the hole currents are both in the same direction, whereas the electron currents are in opposite directions. Okay, and you understand why that is the case, right? You have the picture. Again, no need to memorize, but you need to understand where these things come from. So like I said, go back and review this and make sure you understand this really well. Yes, sir?
Yeah, just so I understand this. So the drift current for the holes is not listed.
Drift current for the holes is JP. So let's look at it. JP drift is here. Okay? But again, if you don't see it, just think about it. The holes have to move in the direction of the field. And the hole is positive charge, so it is the same direction as the current. Okay? So again, just four things to remember, 4 things to understand. So make sure you're very clear on that. Okay, any other questions? No? Okay, let's keep going. So that's the applied field, those are the concentration gradients, and that's the force. Okay, next, we want to also understand what happens to the energy levels. And this will become very important in the next chapter, in chapter 5, when we talk about PN junctions. Okay? Well, we saw this briefly before. When an electric field is applied, the bands bend. Okay? Because the electric field represents a change in potential energy for the carrier, for the electron. Right? So, to review, if you have an electric field this way, the electron moves this way, right? It is trying to minimize its energy. Okay, so if I draw the potential energy as a function of position, it has to go down, right? Because the electron is trying to minimize its energy. The electron flows down the conduction band. Valence band, let's just say. Okay, so the electron flows down. If you recall, and the holes flow up, right? We talked about this. Because the whole potential energy decreases this way. Okay, we talked about that. Keep that picture in mind. So the bands look like that when you have an electric field. So that's the conduction band, that's the valence band, that's the intrinsic Fermi level. That's it. Okay, the electron energy increases along the direction of the field, so it tries to move the opposite way, right? The electrostatic potential is defined in terms of positive charges, so we can write the following. What is the voltage? The voltage, local voltage, is given by the electric field divided by the charge. You have a negative value there because, again, the voltage is defined in terms of electrostatic potential is defined in terms of positive charges. And electric field, of course, is given by the space the rate of change of applied voltage. Right? So you can see the electric field, of course, is also related to the slope of this band diagram. Okay? So we can show that closely, relatively easily here. To relate the field to the band diagram, we have to pick a reference energy level. Let's pick the intrinsic Fermi level. Okay? Remember, the Fermi level has to be continuous at equilibrium. So it's a straight line, so we can use that as a nice reference. Okay, whereas the other things can have discontinuities. The valence band and conduction band, as we'll see later on, can have discontinuities. Whereas the Fermi level cannot have discontinuities. So that's a Fermi level is a good reference energy level. So you can see from this equation that the electric field is just the space rate of change of the potential. And that can be written as space change of rate of the intrinsic Fermi level divided by Q. And basically you'll get that the electric field is also the slope of the Fermi level, or the slope of the band diagram in a homogeneous material. Okay? So if I increase this field, these bands will bend more. If I decrease the field, the bands will bend less. Okay? So remember when we were doing our Hall effect measurements and so on, we applied a field, we applied a voltage. That also meant that you were bending the band. Okay? And we'll come back to this again, but it's an important concept. So again, to summarize, we saw this before, electrons drift downhill, whereas, just to reiterate, the holes go uphill. Okay, because the energies for the holes increase downwards, right, if you recall. Electron energy increases upward, hole energy increases downwards. And the holes are also trying to minimize the energy, so it goes uphill. Okay, now there's a very important relation that we need to understand, which is called the Einsteins Relation. It has to basically do with the interrelationship between the drift and diffusion. So drift, of course, is determined by mobility. Right? Mobility is the rate of the velocity of the electron in a given electric field, whereas diffusion is determined by what's called the diffusion coefficient. It turns out that they are fundamentally related, and that is called the Einstein relation. Okay? To derive this is very straightforward. We start with it's applicable at equilibrium. At equilibrium, there should be zero net current. Okay, no electric field is applied. There's no current. Very straightforward. So if you have any carrier concentration gradient, any concentration change that is set up, you will, of course, have a diffusion current, but that diffusion current must be balanced by some built-up field, much like the Hall effect. Okay? Which means, so let me restate this because this is also an important thing to understand. Okay, imagine the semiconductor bar. Okay, and locally, let's say you generate electrons and holes. Okay, proton-hole pairs. Of course, the electrons and holes will diffuse in all directions. So let's just look at one side first. Okay, so the electrons diffuse this way, the holes diffuse this way. The current of this, so if I draw the current, the electron current is this way, and the hole current is the same direction. Okay, at equilibrium, of course, this cannot happen. Right? You cannot have when everything is died down, you cannot have a current flowing, and you don't have an applied field. Which means that this can happen, by the way, because you might have a concentration gradient of two different materials sitting next to each other, which is the p-n junction, which we'll talk about next class, in chapter 5. Okay, so imagine that you have a concentration gradient which exists, and it's maintained somehow. Okay? Actually, let's make that explicit, because it's a little bit abstract the way I said it. So, imagine two different materials. Okay? This is n-type, this is p-type, and that's a p-n junction. We'll come back to this. This is a fundamental device in semiconductor physics. Okay? Lots of electrons here, very few electrons here. So of course electrons will flow here, right? That's a concentration gradient, right? Very high. So if I draw n as a function of x, it's very high here and very low here, right? And if I draw p as a function of x, it's very high here and low here. Pretty straightforward. So the electrons will flow here, let's call that n, and the holes will flow here, right? But at equilibrium, no flow can happen. No currents can flow. Which means that this flow must be balanced by something else. And that something else is essentially a built-in electric field, which appears just like the Hall effect. The electric field appears, which prevents this flow to happen. So in this case, of course, to prevent the electron flow from going this way, you apply a field. The field appears this way, right? So it will force the electron to go back. So this field will also oppose these holes. It will force the holes to go back. So this built-in field, and we'll talk about how this appears in the next chapter. This built-in field opposes the diffusion. Of course, this built-in field means there's drift, right? The field gives rise to drift. So this drift balances the diffusion that happens. That's the equilibrium condition. Okay? Which means, of course, at equilibrium that the diffusion and drift parameters must be related, fundamentally. Nothing to do with any particular situation. Yeah?
That's why between M and E junctions, you'll have the capacitance sometimes.
You will always have a capacitance, yes, because there's always a field. But we'll talk about that when we talk about the devices. Okay? So essentially what this means is that if you look at these equations, okay, there's no field, so we can drop these terms, right? Pretty straightforward. You will have these two terms. Oh, sorry, you cannot drop them because you have a built-in field. You can calculate what the built-in field is by just setting these terms to 0. Each of the individual currents have to go to 0. The whole current and the electron current. Okay? And that's what we'll do. So for holes, let's do it for holes. For holes, it's very straightforward. Look here. You set that equation to 0. Okay, and then you can calculate what this built-in field will be, which is shown here. Okay? That's that equation. Oops. Okay, that's the equation on the top. dP over mu p times 1 over p dP over dx. Okay. Again, just to recall, that comes from here, right? So if I, right? Let's erase some more. So Q, P, mu p, what is this? E should be equal to Q dP over dx times dP. Right? That's how we did. Okay. That leaves just 1 over P. Okay. Pretty easy. That's what's here. Now, remember, this is equilibrium. So we know what the concentrations are. So we know what this term is. Okay? This is the concentration at equilibrium, so you could put a 0. So P naught is related to the intrinsic Fermi level. Right? We know this. And it's, what is that? It's basically an I, which is the intrinsic concentration, times e raised to, in the case of holes, it is E I minus EV divided by KT, right? I think. No, Fermi. Okay, forgot that. Okay. Yes, EI minus EF. This is the intrinsic Fermi level. Sorry, EI is the intrinsic Fermi level. EF is the Fermi level of that particular material. Okay, let's think back about this a second. Intrinsic Fermi level is the Fermi level of the undoped semiconductor. The Fermi level EF is the Fermi level of the doped semiconductor, in this case, holes or what, or p-type or n-type or whatever it is. Okay, it's either closer to the valence band or closer to the conduction band. EI is close to the middle of the band gap. Okay, that's the basic part. Okay, so now we can take that equation and plug it in to there, and we can get that. Okay. I assume you can do this. It's not that difficult. So put that in here. Put that also in here. Do the derivative. Okay. Once you do that, you will get this expression for the electric field. So the built-in field is now dependent on dP over mu p, which are constants, material constants. 1 over kT, again, constant and depends on temperature. And the gradient of the difference between the intrinsic Fermi level and the actual Fermi level. Okay? Or in other words, this is the slope of the band, right? Think about it. Because EI is just a reference energy level. Okay? EI minus EF is essentially the band. So it's basically the slope of the band. Which of course we knew that. The built-in field has to bend the bands. So the slope of the band must be the built-in field, right? In other words, if I draw it, I'm going to give you a preview from the p-n junction using this logic. If I may go back to the p-type and n-type, so let's say p-type, let's say n-type, p-type, and they were sitting next to each other. We said that there will be an intrinsic field which is this way, which means that if I were to draw the bands, okay, for the n-type, okay, remember we actually did this before, and you will appreciate this more now. Look at the conduction band, valence band. For the n-type, where is the Fermi level? We did this before, so I know everybody should know this. Close to the conduction band, yeah, so it's right there, okay? And of course, the Fermi level has to be continuous across, we saw that too. And here, it will be closer to the valence band. Right? Because it's n-type. So you see what's happening? These have to be continuous, so they bend. And of course, this bending is that field that we just talked about. So if you put two things together, they get to equilibrium, a field appears, and of course that bends the bands. This is very, very important. In fact, we will spend a lot of time on this starting next week. Okay, but you see that from the equation, that is that field. And that's related to the slope here. Now, this, of course, is EF. Right? This is EF. Now, EI is, of course, here and here. And it will bend. Now, this is not so meaningful. We'll talk about that later. EI is just the middle of the band, pretty much. Right? So if I talk about EI minus EF, it is the slope here, because EF is a constant. You can just throw it out for the sake of argument. Right? It's just the slope here. Of course, we knew that, because slope is related to the field. Okay? And that's all this equation is saying. Okay? Now, this, of course, is 0. Right? We know that shouldn't change. It's a constant. So, dEF over dx will be 0. This is what we saw last class, right? Under equilibrium, the Fermi level cannot have any change in space. So that term goes to 0. This term basically becomes that. And we know that the field is also related to this from what we just saw. Right? The field is related to the slope of the band, or the intrinsic Fermi level. So if you equate these two, what do we get? So what this is saying is 1 over Q dEI over dx. That is the field, EI being the intrinsic Fermi level. The slope of the intrinsic Fermi level is the field. Is equal to dP over mu p times 1 over Q, just this thing. Okay? I forget KT. No, I did, because it needs to be converted into the. Okay? Is that clear? So the right hand side just comes from here. Okay? This thing is from here. Okay? And this thing is what we saw just in the last slide, and it's also here. Okay, so now you see what's going on. This goes away, this goes away. Okay, now you see that these are all constants. This is the electronic charge, that's a material constant, that's a material constant, K is a constant, K is temperature. See, there's a fundamental relationship between mobility and diffusion. That was a very important understanding of semiconductor physics. In fact, this is more general than semiconductor physics. This is true for all mechanics, it turns out, and that's why Einstein actually derived this even before any semiconductor physics existed. Right? This was derived for just statistical thermodynamics. That's why they call it Einsteins Relation. So essentially the relation is very simple. If you know the diffusion, you can calculate mobility. It's as simple as that. D over mu is KT over Q. KT over Q, by the way, at room temperature is nothing but about 26 millivolts. Right? K times T at room temperature is about 26 millivolts. Okay, if you take at room temperature, T is 300 Kelvin. In case the Boltzmann constants, you multiply it. Okay, so again, what this means is that if you know mobility, you can calculate diffusion. If you know diffusion coefficient, you can calculate mobility. So it's extremely useful. Again, remember, the goal here is to calculate current. So in order to calculate current, we have 4 terms we need to worry about, as we saw in that picture that I want you to understand. And the 4 terms depend only on these 2 parameters, mobility and diffusion coefficient, of the 2 carrier types. That's all. Once you know these 2, you can know all the currents. So what this relation tells me is that I don't really need to know 4 things, I only need to know 2 things. Okay, if I know mobility or the diffusion coefficient for each of the carriers, I know everything. Okay, and you will see this in your problem sets, I think. Okay. Okay, so this is basically what I drew before, but more explicitly. This is a p-n junction, so we have a p-type material and an n-type material sitting in intimate contact. The carrier concentration leads to a built-in electric field. Again, I guess I answered the question. So the question was, which way is the field pointing? So I guess you can think about it yourself. I know I answered it, and it's there, but think about it yourself. The way to think about it is the following. Okay, the logic is the following. There's a lot of holes here. There are very few holes here. So of course the holes will want to go from here to here, blue to red. Okay? And the purpose of the field is to maintain the equilibrium, meaning the purpose of the field is to prevent the holes from going from blue to red. So of course the field has to point from red to blue. Right? It has to oppose the motion of the holes. And the same conclusion can be reached by thinking about electrons. So there's lots of electrons here, very few electrons here. So electrons will diffuse from red to blue. Okay, so the built-in field must oppose that motion, which means the field has to point from blue to red, because electron motion is opposite to the field. Okay, I know it's a little bit confusing when you first hear it, but you need to think about this and understand this, because this will be the basis of everything we'll talk about for a few weeks. Okay, so in this case, which way is the field pointing? Is it from n-type to p-type or p-type to n-type? Yeah, n-type to p-type. Okay? Okay, so make sure you're able to follow that logic. Okay, so the last topic we need to cover today is one thing we have ignored completely so far is, so by the way, this is the start of chapter 4, so for those of you who want to follow it in the text. And in chapter 4, this is what I meant in the beginning. I'm changing the order a little bit. So in the beginning of chapter 4, the text talks about optical generation of carriers, which we will talk later about. So I'm going to talk more about the latter part of chapter 4 first. Okay? So if you follow it, but it'll be obvious. Okay, so the thing we have ignored in diffusion. So remember, we had a pulse of electrons and they diffused. But we ignored one thing, which is recombination. Remember, anytime there's a generation of electron-hole pairs, they need to be balanced by the recombination of the electron-hole pairs at equilibrium. Remember, we talked about generation rate equal to the recombination rate and so on. So whenever there are electrons and holes, there is also a chance that they will recombine and cease to exist, essentially. Okay? So recombination essentially is a combination of the electron and a hole, and they cease to exist. They annihilate each other, essentially. And that's shown pictorially here. So if you have an electron floating around in the conduction band, you have a hole floating around the valence band, they can recombine here. Essentially what that means is that these two silicon atoms can trap them, and they form a bond. They're trapped. In other words, and that can happen with loss of energy, because the conduction band electron and the valence band hole has energy, excess energy. That energy has to be released. And that can be released, in the case of silicon, usually as heat into the crystal lattice. In the case of gallium arsenide, it can be light, right? You can have photons coming out. So from the energy band perspective, if I just talk about the n-type, you have electron sitting here, and you have a hole sitting here. What that means is that the electron basically comes down to the valence band, the hole basically disappears. And that excess energy is released as heat. Okay? And the physical reality picture is shown here, where they actually just get trapped by silicon atoms. Two silicon atoms form a bond, essentially. Okay? There's a probability of that happening, and we need to account for that in our current. If you want to rigorously calculate current, we need to account for that. Because what does that mean? When you have recombination, the carrier concentrations have changed, right? Because you've taken away an electron, you've taken away a hole. Of course, it affects the drift current, right? Because the N and the P have changed. Of course, it can also affect diffusion, because it changes the concentration gradients as well. So you need to account for this as well. Okay? And that's what we will do. Okay, so we'll get this started. So if there are charge carriers, recombination happens, so we need to account for it. So imagine a bar semiconductor here. Okay? So it is a p-type material in this case. Is it? I think I forget. It might be n-type. We'll come to that. But imagine a small region here, okay, whose thickness is delta x, and the area is A. Okay? We're looking at a small region. The whole current coming in is Jp, and the whole current leaving is Jpx plus delta x. Okay? And this is, for now, this is just diffusion. So we'll ignore drift for the sake of time being. Okay? The rate, so if you look only in the shaded region, the rate of increase in hole concentration is given by the rate at which the holes come in minus the rate at which the holes leave. Okay? Pretty simple. So it's Jp of x minus Jp of x plus delta x divided by q, because you need the number of carriers, divided by delta x, because you're looking at per unit distance. Okay? The idea here, of course, is to look at how the concentration gradient is changing. Okay? You can need to consider recombination, because there's the chance that the holes will recombine with electrons within that volume, and that's given by this last term here, so-called recombination rate. Okay? Delta P, the recombination rate, which we saw before, is proportional to the number of available carriers, excess carriers, which in this case is this delta P, and inversely proportional to so-called lifetime of the carriers, 1 over tau P. Okay? We saw this before. So that's that term, and it's negative because it's getting rid of holes. So you see the concentration of holes within the shaded region is going down. Okay? So rate of hole buildup is the increase of hole concentration in this region per unit time minus the recombination rate. Okay? And this is a so-called continuity equation for holes. Okay? And we can write it the following way: is that rate of change of the hole concentration is a function of time, or the rate of change of hole concentration is equal to the spatial change of the hole current minus the recombination rate. Okay? This, of course, in differential calculus just becomes that. right? And of course, these are partial differential equations because you have space and time to worry about. That's the complexity of the diffusion. The diffusion, of course, changes with space, right? Because the diffusion spreads. But also time dependent because the spreading happens over time. So you have to worry about both space and time. So diffusion problems are hard to solve in general. Okay? And the corresponding continuity equation for electrons is shown here. Same thing. Okay? I think we'll stop here. We need to review this on Thursday because it's a little involved in terms of math. Okay. So again, remember there's no class Tuesday, so don't show up. And Thursday the class is delayed to 9:45. Okay. And check the website before you come, because I'm flying in at 9 o'clock. So if I'm delayed, I'll post it on the website. Yes? Yes. So there's a review session on Friday and Monday. And the review problems from chapter 4, which is we just started, I'll post them online. But most likely he will go over chapter 3 still. So that's related to your problem set 2. Okay?